Dear friends, welcome you once again for today's discussion. Today we are going to discuss about flow of steam through nozzle. What is a maximum flow rate and what is a velocity coming out from the exit and what are conditions of the maximum flow rate. And earlier in our previous class we have discussed about nozzle efficiency, what are conditions of isentropic flow and actual flow and nozzle efficiency and static energy equations through nozzle. So today we are going to discuss what is the exit velocity and what is condition of maximum mass flow rate and what will be velocity of the steam during maximum mass flow rate and where velocity will be sonic. All these things we are going to discuss here. This topic is going to be very interesting. So please I will request you personally that you should like and subscribe this my channel so that timely we will be motivated more and more to prepare some good topics for you. And this topic is interesting from competitive examination point of view. For example, in CAT examination and in engineering service examination and BARC examination and so many public sector examinations, you will always type you will always find 3 to 4 questions from this topic and one full question that is a 50 marks question that you will get from this topic from nozzle or steam turbine. So let us start here. One thing that I will use here momentum equation for steam flow through nozzle. That equation I will directly use here. That is simple to remember because this derivation of this equation is very complex one. I think it is wastage of time to derive this equation. In later stage we will derive this equation and I will share a video for derivation of this equation and explaining all these things. So now let us start. What is the velocity coming out from the exit of the nozzle? So again we will draw nozzle here. Simple converging-diverging nozzle just to show flow rate. This is inlet condition and this is a cross section material construction. This one is inlet condition 1 and 2. So here velocity is C1, specific value V1 and pressure is P1, area is A1, inlet area. And this is the exit side, corresponding value will be C2, specific volume V2 and pressure P2 and area A2. So for this condition we have to write equation and we will use momentum equation. Momentum equation, that is a change of gain in kinetic energy C2 square minus C1 square by 2 equal to integration of volume VdP P2 and limit are P2 P1. Limit are P2 because here pressure is P2, initial pressure is P1 and P2 is less than P1, that's why we have taken limit P2 to P1. And if we draw this equation, this is momentum equation, this is a PV diagram and expansion will follow PV to power n equal to constant. Polytropic expansion is a polytropic expansion, n is a polytropic index. So let us see how it varies. This is a expansion curve and initial stage is P1 and final stage is here is P2. Expansion is taking from P1 this equation PV to power n equal to constant. Let us see, suppose this is the condition. We will take a small strip that is pressure difference dP and here volume is V. So that you see here VdP. This is a VdP. This area is VdP. Area of this strip is VdP. And so we integrate and we follow this equation PV to power n equal to constant. So PV to power n equal to P1 V1 to power n equal to P2 V2 to power n equal to C. So V equal to C upon P to power 1 by n. V equal to C upon P to power 1 by n. Putting this value in this equation and we then solve. So using this equation, let us solve this equation. So C2 square minus C1 square by 2 equal to VdP P2 to P1 VdP replacing V. by c to power c upon p power 1 by n and dt, and taking out c to power 1 by n out, this is a constant, and p2 p1 and p to power minus 1 by n and dp. Integrating this one and putting values of the limits. So c to power 1 by n and p to power minus 1 upon n plus 1 upon 1 minus 1 upon n. Taking limit p2 to p1. So simplifying this one, c to power 1 by n upon n minus 1, and limit will be p1 to power n minus 1 upon n minus p2 to power n minus 1 upon n. Multiplying this by constant, so n upon n minus 1, c to power 1 by n, p1 to power n minus 1 upon n minus c to power 1 upon n, p to the power n minus 1 upon n. So now take value of c to power 1 by n. C to power 1 by n. C to power 1 by n, you can take two values here. C to power 1 by n, from this you see c to power 1 by n equal to p, that is equal to v1, p1 to power 1 by n equal to v2, p to the power 1 by n. Any value you can take according to your requirement. Because here we want to take a c to power 1 by n in terms of v1 p1, and here we want to take c power 1 by n in terms of v2 p2, so that we get simplified equation. So n upon n minus 1 v1 p1 to power 1 upon n and p1 to power n minus 1 upon n minus p2 minus v2 p to the power 1 upon n into p to the power n minus 1 upon n. Now simplifying this one, simplify this, we get equation c2 square minus c1 square by 2 equal to n upon n minus 1 p1 v1 minus p2 v2. Most of the time you see that inlet velocity here is very small compared to C2. C1 is very small compared to C2. So C1 can be neglected. So it again simplified, C2 square by 2 equal to n upon n minus 1 bracket p1 v1 minus p2 v2. So let us see here another. We have derived equation c2 square equal to n c2 square by 2 equal to n upon n minus 1, taking p1 v1 minus p2 v2. So c2 square in bracket, you will see c2 equal to 2n upon n minus 1 in bracket, taking common p1 v1 common, you will see 1 minus p2 v2 upon p1 v1 under root, whole of the under root. This is equation that is determine the velocity of exit from the nozzle. And we know that again we can simplify v2 by v1. You know p1 v1 to power n equal to p2 v2 to power n. So v2 by v1, here you see v2 by v1 equal to p1 by p2 power 1 by n. Putting this value here, so again we simplify some logical form, 2n upon n minus 1 p1 v1 in bracket 1 minus p2 upon p1 into p1 upon p2 to power 1 by n. Now simplifying, p to power 1 by n go up and p1 to power 1 by n go down, and simplify this, that will be equal to under root 2n upon n minus 1 p1 v1 in bracket 1 minus p2 by p1 to power 1 minus 1 upon p2 1 minus 1, n minus 1 upon n minus 1 upon n. This is a final equation for the velocity. And again you can simplify this one. If we but here let us see, this is a final velocity c2 equal to under root 2n upon n minus 1 P1 V1 in bracket 1 minus P2 by P1 power n minus 1 upon n. This is equation. And now finding velocity. Already we have defined that velocity m equal to a1 c1 upon v1 equal to a2 c2 upon v2. This is a continuity equation of a flow through nozzle. Continuity equation of flow through nozzle. So here we want to calculate mass flow rate at the exit, or both will be same. So we use this because we have calculated C2. So we will find m equal to A2 upon V2 and C2 we put here value 2n upon n minus 1 in bracket P1 V1 is also there, P1 V1 1 minus P2 by P1 to power n minus 1 upon n. This is a value, and let us see, because here V2 is also there, so we have to find out V2 in terms of P1 V1. You know P1 V1 equal to P2 V2 to power n. So V2 equal to V1 and P1 upon P2 power 1 upon n. So V2 square equal to V1 square P1 upon P2 power 2 by n. Taking value inside the bracket, so it will become V2 square. So now m equal to A2 by A2 under root 2n upon n minus 1 P1 V1 upon V2 square. So V1 1 you have to remove 1 V1. In bracket you will take 1 minus P2 by P1 to power n minus 1 upon n. Bracket close. So you have to put V2 here already. So taking V2 inside the bracket and putting value of P1 V2 equal to V1. So putting value of V2 here and taking V2 inside, because V1 already only V1 will remain, and take this value inside. So let us first put here 2n upon n minus 1 P1 upon V1 power P1 upon P2 to power 2 by n in bracket 1 minus P2 upon P1 to power n minus 1 upon n. Taking this value inside the bracket and simplifying this one, we will get A2 under root 2n upon n minus 1 P1 upon V1. This will become, when it will go inside, this will reverse, numerator will become denominator. So it will be equal to P2 upon P1 to power 2 by n minus, here 2 by n will add here, so n plus 1 upon n minus P2 upon P1 power n plus 1, writing here this equation. So m equal to A2 under root 2n upon n minus 1 P1 upon V1, and here you will find P2 upon P1 to power 2 by n minus P2 upon P1 power n plus 1 upon. This is a final equation for finding out mass flow through the nozzle exit. If it is a mass flow through the nozzle exit, this is a final equation. Now see that this is a mass flow rate through nozzle exit. What are the conditions of the maximum discharge? So see here inside the bracket, this is a main, this is a P2 by P1 is a ratio. We can consider P2 by P1 we can take equal to ratio R. Equation will simplify m equal to A2. This is a constant value, and 2n upon n minus 1 P1 upon V1, and R to power 2 by n minus R to power n plus 1 upon n. So you see that what is on what parameter? R is the main parameter, because P1 and V1 are initial pressure and volume condition. Specific volume condition, M is a constant for given condition of the steam. P2 is executed, this is a constant. So depending upon the M depend upon the R pressure ratio. So dm for maximum for maximum discharge, M maximum, dm by dr should be equal to 0. For maximum discharge, dm by dr equal to 0. So differentiating the whole quantity inside the bracket with respect to r. So now writing this one here. Now see, dm by dr equal to 0 means d upon dr bracket में bracket r to power 2 by n minus r to power n plus 1 upon n. Differentiating this one and equal to 0. So 2 by n r to power 2 by n minus 1 minus n plus 1 upon n and r to power n plus 1 upon n minus 1 should be equal to 0. So now 2 by n r to power 2 minus n upon n equal to n plus 1 upon n r to power n plus 1 minus n upon n. N here replace, n from here replace. So 2 upon n plus 1. 2 upon n plus 1 equal to r to power 1 by n upon r to power 2 minus n upon n. Simplifying this one, r to power 1 minus 2 and plus n upon n, that is equal to r to power n minus 1 upon n. R equal to 2 upon n plus 1 and power n upon n minus 1. This is a condition of maximum discharge. This is a condition for maximum discharge, means R equal to P2 by P1 equal to 2 upon n plus 1 and n upon power n upon n minus 1. This is a condition of maximum discharge, and this is a condition of maximum discharge. This is a very, very important term that this is you can say gateway of the steam turbine and nozzle. Find out condition of maximum discharge. N equal to 1.135 for saturated flow, and N equal to 1.3 for superheated flow, and this will also provide condition of the pressure at the throat. When pressure at the throat become P2 critical, then P2 upon P1 you have to find out pressure at throat by using this equation, and you can also find out per exit what is the mass flow rate. So now what is now second thing is that when there is a critical mass flow rate, when there is a maximum mass flow rate, and putting this value condition P2 by P1 in equation of the mass flow, you can find out maximum mass flow rate also. If we want what is the maximum mass flow rate, putting this value of P2 by P1 in equation of the mass flow rate, you can get a mass flow rate. So now next condition, what will be condition when there is a mass flow is maximum? At what is a velocity of the steam at throat, velocity of steam when mass flow rate is max, means choked flow condition. In choked flow condition, what will be velocity of the steam? So let us see very simple equation. So already we have calculated m equal to A2. We have calculated m equal to A2 and under root 2n upon n minus 1, and that was equation, simple equation, P1 V1, again taking P1 V1, P2 V2, because we want to calculate what is the speed of the steam, velocity of steam when there is a maximum discharge. Taking P2 V2 common here, A2, and taking P2 V2 common here, 2n upon n minus 1 and P2 V2, and here P1 V1 upon P2 V2 minus 1. So here we have to replace V1 V2, P1 V1 to power n equal to P2 V2 to power n. So V1 upon V2 equal to P2 by P1 to power 1 by n. Putting this value in this equation, so m equal to, this is I think this is not m. This is just C2. This one not M, because I have not divided. This is C2. This is a size C2. This was C2 velocity. if we divide this equation by small v1, then it will become, here also we have to replace it because there is no, we are only considering c2, so no m. This is c2 equal to 2n. This is not, we are calculating c2. What will be condition, what will be velocity of the steam at thought when mass flow, condition of mass flow rate? So what is the velocity of steam? So steam velocity is given by this equation, not a2 and v2 will come, because m is equal to a2 c2 upon v2. So these two terms will replace, only we get this term. So now putting value of v1 by v2 here in this equation, so this will be equal to 2n upon n minus 1 p2 v2, and in bracket p1 upon p2 in multiplication, here putting value p2 upon p1 to power 1 by n minus 1, simplifying this one, so we will get 2n upon n minus 1 p2 v2 in bracket p1 upon, this will be equal to p2 upon p1, p2 upon p1, p2 upon p1 power p2 upon n 1 minus p2 upon p1, it will go 1 minus n minus 1, so 1 minus n, 1 minus n upon n minus 1. This is equation. So now putting condition of maximum discharge, already we have taken p2 by p1. Here putting condition of maximum discharge, 2 upon n plus 1 and n upon n minus 1. So putting value of p2 by p1 in this equation, so c2 equal to under root 2n upon n minus 1 p2 v2, and that will be equal to here 2 upon n plus 1 power n upon n minus 1 and to power n minus 1 upon n minus 1. Removing all these values, you will get simplified version, that is equal to 2n upon n minus 1 p2 v2 in bracket 2 upon n plus 1 minus 1. So simplifying this one, you will get an equation 2n upon n minus 1, 2n minus n minus 1 p2 v2 2 minus n and minus 1. So it will become equal to that is equal to 2n upon n minus 1 into p2 v2 1 minus n, 1 minus n minus 1. I think there is some typological error I have committed here in calculation of this equation. I think p2 v2 have taken 2n upon n minus 1 and 2 and plus 1 and n upon n minus. Here we have put value 2 upon n plus 1, 2 upon n plus 1 n power n upon n minus 1 power n minus 1 upon n. It will be removed. You will get only 2 upon n plus 1. So 2 upon n plus 1 minus 1 and 2 minus n minus 1. So you get 1 minus n and here n minus 1. Simply you will get after solving all this, you will get n p2 v2. If you m p2, that is a velocity of the sonic. This is a sonic velocity. This is a sonic velocity. When you clearly solve, you get this term n p2 v2, not here 2. So sonic velocity, and later I will further clarify what is this sonic velocity. So one thing is quite clear, that after this discussion, that when there is a steam flowing maximum discharge condition, at maximum discharge condition, you will find at maximum discharge condition, velocity of the steam will become velocity of the sound. If we draw a graph, here we draw a graph. This is a velocity, and this is the pressure ratio, P2 by P1. So this is a, suppose this is a steam velocity, and this is a sound velocity. This is the velocity of sound. At this point, this is A and this is a C. So both will become same. At this critical pressure ratio, P2 by P1 equal to critical pressure ratio. Critical pressure ratio. At this point, it is equal to 2 upon n plus 1 to power n upon n minus 1. At this condition, sonic velocity of the steam velocity will become sonic velocity. This is known as a choked flow conditions. Means at thought, velocity of the steam will become velocity of the sound. So ratio of this m equal to a by c, m equal to c by a equal to 1. A is a velocity of sound and c is a velocity of the steam. So this point at this pressure ratio, steam flow through the throat. This is a steam flow through the throat. Suppose this is a convergent divergent. Now at this point, this is a divergent part and this is a convergent part. This is a throat. At this point, and pressure ratio that is defined by P2 by P1, and this is the pressure ratio P2 by P1 equal to R. So maximum mass flow rate will take place at this throat condition, and velocity will become velocity of the sound. Steam velocity will become velocity of the sound. So that is a C will become under root n P2 V2, under root n P2 V2, and this is known as the velocity of sound. So in my equation derivation, there was a 2 coming here. So that is I will define why there is some mistake. But one thing is clear that at sonic condition, at maximum mass flow rate, velocity of steam will become velocity of the sound, and the Mach number will become here 1. And this is the condition. This condition is known as a choked condition. And there is no any further increase in mass flow rate when you decrease the critical pressure ratio. This pressure ratio, there is a further decrease in, because it is here it is 1 and continuously it will go down. So no effect on mass flow rate will depend. Mass flow rate become after that it will remain constant. So thanks for watching, and in next class we will discuss about what is a maximum discharge in terms of some empirical formula, and what will be relationship between area Mach number and area Mach number and velocity. Area Mach number and velocity, that is the most important equation we have to learn and we have to apply. Thank you very much for watching, and please like and subscribe. Have a nice day.